Hi, this video is going to be covering VSEPR theory, doing some examples, and giving some demonstrations. Now first, what does VSEPR stand for? Well, it stands for valence shell electron pair repulsion. This means that in compounds, electrons are naturally repulsed from each other and get as far away from each other as possible. We'll be using this theory in this video to turn 2D drawings of compounds into 3D molecular shapes. Here is the first example, SiO2. Before we can draw the electron geometry, we have to solve for it. Now, Si, or silicone, has 4 electrons. 2 oxygens both have 6 electrons each. Therefore, 4 plus 12 is 16, and the compound has 16 electrons. But each molecule wants 8 electrons each, and therefore, the compound wants 24 electrons in total. Therefore, it will have 4 bonds and 4 lone pairs in the drawing. Here is the electron geometry. Silicone is in the middle, and both oxygens are on the outside. Both oxygens have 2 lone pairs each, so that it is completely balanced, and each molecule has 8 electrons each. This electron geometry is linear because there is a center atom and 2 atoms surrounding it. The molecular shape is also going to be linear because there is a center atom and 2 atoms surrounding it. The bond angle is going to be 180 degrees so that the electrons are as far away from each other as possible.
It's a three-dimensional version of SiO2. This is its molecular shape. It has a center atom and 2 atoms surrounding it with an 180 degree bond angle.
Here is the second example, BF3. Now, since you already know how to solve for the electron geometry, you know that there's going to be 4 bonds and 8 lone pairs. Here is the drawing of the electron geometry, with boron in the middle and 3 fluorines on the outside. Each molecule is balanced with 8 electrons. Now, the electron geometry is going to be trigonal planar because there's a center atom with 3 atoms surrounding it. The molecular shape is also going to be trigonal planar because there's a center atom with 3 atoms surrounding it, and the bond angle is going to be 120 degrees.
This is the molecular shape of BF3. It has a center atom with 3 atoms surrounding it, and a bond angle of 120 degrees, so that the electrons of each atom are as far away from each other as possible.
This is the third example, O3. O3 has 3 bonds and 6 lone pairs. Here is a drawing of the electron geometry, with 1 oxygen in the center and 2 oxygens surrounding it. Each oxygen is balanced with 8 electrons. Now, the electron geometry is going to be trigonal planar because the center atom is surrounded by 3 groups of electrons. Here's the first one, here's the second one, and here's the third one. Now, the molecular shape is going to be bent. What does that mean? What makes a molecular shape bent? It occurs when lone electrons pairs replace an atom in a molecular shape. The lone electrons repulse the other atoms more and slightly push them together. This makes for a smaller bond angle and therefore a bent molecular shape. So back to this example. This lone pair group of electrons is going to compress these 2 atoms together. That's what makes it bent. The normal bond angle of a trigonal planar molecular shape would be 120 degrees, but because it's bent, it's going to be about 116 degrees.
This is what the molecular shape of O3 would look like, 3-dimensional. Now, there's a pair of lone electrons right here that is compressing these 2 atoms together and making for a smaller bond angle, with the center atom and then these 2 surrounding.
Here's the fourth example, CBr4. CBr4 has 4 bonds and 12 lone pairs. Here's a drawing of the electron geometry, with carbon in the middle and 4 bromines surrounding it. Now, each molecule is balanced with 8 electrons. Each of these lines that represents shared electrons, I want to clear something up in case you were confused. Here's what I pictured the inside of the lines to look like. each line contains a pair of electrons. And between each molecule, that's truly what is shared, a pair of electrons. Now, back to this example. The electron geometry is going to be tetrahedral because there's a center atom with 4 atoms surrounding it. The molecular shape is also going to be tetrahedral because there's a center atom and 4 atoms surrounding it. The bond angle is going to be 109.5 degrees.
The dimensional version of CBr4 would look like. Once again, it's tetrahedral. It has a center atom with 4 things surrounding it, and a bond angle of 109.5 degrees.
On to the 5th example, PF3. PF3 has 3 bonds and 10 lone pairs. Here's the electron geometry drawing of PF3, with phosphorus in the middle and 3 fluorines surrounding it. Each molecule is balanced with 8 electrons. Now, the electron geometry is going to be tetrahedral because the center atom, phosphorus, is surrounded by 4 groups. 1, 2, 3, 4. However, the molecular shape is going to be a little different. As you can see here, there's a lone pair here that compresses these 3 surrounding atoms together. This, you would think, is bent, except there's a specific term for when there's a center atom, 3 atoms surrounding it, as well as a lone pair, and it's trigonal pyramidal.
This is the molecular shape of PF3. Once again, it's trigonal pyramidal, and it has a lone pair up here that is slightly compressing together these 3 atoms right here to a bond angle of about 107.
Last but not least is example number 6, OF2. OF2 has 2 bonds as well as 8 lone pairs. Here's the electron geometry drawing of OF2, where oxygen is surrounded by 2 fluorines. Now, as you'll see, the center atom is surrounded by 2 lone pairs as well as 2 bonds. This is going to make the electron geometry tetrahedral because the center atom is surrounded by 4 groups. 1, 2, 3, 4. The molecular shape, on the other hand, is going to be bent because the center atom is surrounded by 2 other atoms as well as 2 lone pairs. Now, these lone pairs are going to compress these 2 atoms together and therefore make it bent. The original bond angle of a tetrahedral shape would be 109.5 degrees, but here it's going to be about 105 degrees.
Here's the 3D molecular shape of OF2. Once again, it is a bent tetrahedral shape. There would be 2 lone pairs right here that are compressing these 2 atoms together to make a bond angle of about 105 degrees.